Regression analysis is synonymous with econometrics. It's kind of the same thing. So you're going to be doing a lot of regression analysis. So let's talk about what is regression analysis? What is it used for? When you tell a computer to do this kind of analysis, what's going on underneath the hood? And then what's going on outside of the hood, like when it gives you the results, like in a table. What does that table mean? We're going to focus on a couple key portions of that table. Then we're going to look at, in broad strokes, what does that table actually tell you about the data and what can you use that output for? Things like prediction and things like that. And then we're really going to get a little bit more narrowly focused into what do we mean by linear regression? Does it mean we're only doing straight lines? So what is regression analysis? Essentially, it is taking a scatter of points, some x variable and y variable. So we got our x right here and our y variable. And you put them together and we got a whole bunch of different observations. Each dot there is an observation. So you have this scatter plot. And you'd like to kind of summarize the relationship between x and y. Now, one thing we can tell from this scatter is that there seems to be some kind of positive relationship. Now, there's a lot of scatter around that line, but that line pretty much reflects the fact that, on average, as x increases, y also tends to increase, which is to say that the line has a positive slope. Now, we'd like to get the best possible summary of that scatter plot. So there's going to be one line that best fits that scatter of points. Now we'll put off what exactly we mean by best fit until a couple slides from now. For now, just think of it as it's the best line that goes through that cloud of points. So what is regression analysis? It's fitting a line to a scatter of points. Now you tell the statistics software that you're running, whether it's Stata or Excel or SAS, SPSS, R, whatever, to regress Y on X, and it's going to spit out some computer output. Almost all of the statistics software will spit out output that looks just like that table. The font may be different. The order of some of the little sub-squares and stuff, these guys here, or this might be, stacked on top, but the output is pretty standard. Now, I told you that regression analysis is fitting a line. In fact, here is that real line that best fits that scatter of points. But where in this mess is there a straight line? Well, turns out that answer is right here. In these two numbers is all you need to define a line. Think about from high school. The equation of a line is y is equal to mx plus b. You have a slope there, that's m, and you have an intercept. That's it. So if you know the intercept and you know the slope, you know the equation of the line. Well, that's what these coefficients actually mean. The coefficient that's attached to the variable x, that's your slope. Notice it's attached to the variable x. So our slope is 2.16. So we have 2.16x plus an intercept. An intercept is a constant, right? It's just a number. It doesn't change. It doesn't vary. And so that's right here where you see constant. The coefficient attached to the constant is, in our case, 57.49. 57.49. That's it. That's our equation of the line. All these other points in that crazy looking table, for the time being, you can ignore them. They're not important for now. You just want to know the equation of the line? Right here. hidden in this column called coefficients. Now, in econometrics, we just rearrange our mx plus b. So rather than mx plus b, we do b plus mx. It's the same thing. And then, b and m is just too, plebeian. We want to sound fancy, look fancy. So rather than b and m, we use a beta 0 for b and a beta 1 for m. It's still just a straight line. The notation is a little bit different. But it's good to use this beta notation because that's what everyone in econometrics uses. So you don't want to run off talking about m's and b's and they'll look at you funny, like you don't know what you're talking about. You're not part of the in crowd unless you start using betas. All right, so what do we have again? Beta 0 is 57.49. Beta 1 is our slope, that's 2.16. Multiply that by x. That is our equation for a straight line. One more time. This line is y is equal to 57.49 plus the slope on x, which is 2.16. That's it. That's our equation for the line. Now we can use that line rather than reporting the scatter of points. See, it's a whole lot easier for you to say, well, the relationship between x and y is this, which fits on a bumper sticker, than to have to give them this entire picture, or even worse, your data spreadsheet. That equation in the box, that's a nice summary of this relationship between y and x. Okay, we can use this to do all kinds of stuff. We can ask, if x changes, how does y change? Or if x is a particular value, what is y? All the things that you do in high school with the equation of a straight line, we can now do on our straight line. Okay. Now just a little bit of terminology because we were talking about betas rather than m's and b's. One thing is common among all statisticians. They're going to use the betas. But the terminology, what they call these betas, now that kind of depends on the field. Some call it stimulus variable and response variable, especially in psychology. Left-hand side variable, because the y is on the left, and right-hand side variable, because the x here is on the right-hand side. Those are common and I think nice. Some call it explained variable. That's what we're trying to figure out, how x causes y, so y is explained by x. Fancy folks talk about regressands and regressors. That language is kind of falling out of fashion because it's really snooty. Covariates is a very common way of expressing x's because your x's covary with y. Much more common is to call them control variables. Right, so you want to know what the effect of x is on y. You're going to tack on a whole bunch of other x-type variables, and you'll call those control variables. Dependent and independent variables. I should write independent here in this list. So y is the dependent variable. It depends on x. So x is the independent variable. You get to change this one. And then y changes as a result. So it's the dependent variable. It depends on x. In computer science, by the way, you'll hear a lot of folks, or data science even, talking about x as their features. So depending on what research articles you're reading or whose blog you're reading, you'll see any combination of these terms. I'll try to stick with y and x because pretty much everybody puts y on the vertical axis and x on the horizontal axis, and that's how we think. Y is mx plus b. You got y's and x's. Why you want to go around messing things up and calling them regressands and regressors? It's obnoxious. So I'm going to try not to do that. Now the other part of that equation, not the y's and the x's, were these guys, the betas. Okay, so what is this beta 0? We said that was the intercept. And beta 1, that is the slope. Beta 1 tells you rise over run, which is to say the change in the y direction, because y is usually on that vertical axis, divided by run, which is to say left and right movement, change in the x variable. So rise over run, dy over dx. That's your slope. So if you ever get questions about how does y change when x changes, everything you need to know to answer that question is in your slope term, your beta 1 term. Your intercept term, which is, by the way, also sometimes called a bias in data science, your bias term is your intercept term. It controls not the slope of the line, but its intercept. So whether you're shifting this straight line up or down. That essentially tells you what is the value of the value of y when x is 0. So let me draw a fresh line here. If we had y is equal to, I don't know, 2x plus 3, then the fact that this intercept is 3, that just means that when x is 0, y is 3. That's it. All right, now, what goes on under the hood? Like when you tell your statistics package to estimate that straight line, what's it doing, and what exactly do we mean by best? Because that kind of sounds like, vague, best. The idea behind regression is that really what we're after is a way to figure out what affects y. We're trying to predict the level of y. X is pretty much just a means to an end. Our goal, our target is y. So when we're thinking about like how good is our statistical model, how good is our line, really what we want to know is how different is our guess, our prediction. How different is our prediction from the data point? So if you subtract those two values, you get the difference between them. All right, so we want some kind of line. Here's a candidate line. And we're going to take every single point, every one of these 20-some points, and calculate the value of the data point. So here, that value happens to be, I don't know, about 350. What we predicted is what goes on here on this solid red line. At a value of 60, we would have predicted here. We would have predicted, I don't know, that looks like around 250. And so the difference between 350 and 250, what's 350 minus 250? That's 100. Right? We subtract straight up and down because what we want to do is focus all of our attention on y, our prediction of y relative to what y actually was. And it's this gap that we're trying to minimize, the vertical distance. But wait, there's more. We have this positive difference here. We have a negative distance here. Negative, positive, negative, negative, positive. Okay, good. So we got to minimize these differences, not just of one data point, but of all data points. So let's add up, let's sum up all of these points. If we have I is equal to 1 to 20, and we have our prediction for point I minus the actual data value for the particular point I could be this one, or this one, or this one, or this one. There's about 20 of these points. All right, so we want to minimize this sum of these errors. And then what we're going to do is actually not just minimize the sum of the errors. We want to minimize the sum of the squared errors. So we're going to take this 100 and we're going to square it. So that's going to become 10,000. Now, why do we square it? Now, there's a lot of historical reasons for that, but I think there's two functional reasons for why we would square these what are called residuals, or these errors. One is, I want to treat an error like an error. I don't want to just say, well, we had a 100 error here and a negative 100 error here, so everything is perfect. And frankly, the reason is that if I have a scatter of points, I could fit this line and the positives would be offset by the negatives, but I could do the same thing with another line like that. And I could still have the positives and the negatives offsetting so that on average that error is 0. But clearly this second line isn't as good as the first line. So if I don't do something to get rid of the fact that these are negatives, I don't get a well-defined answer. I don't get a single output from the computer program. And in fact, I could get something that's absolutely horrible, this negatively sloped line. Now, the obvious solution to us is to take the absolute value. Just drop the negatives. I gotta say, in a lot of very modern statistical work, that's what's done. But in most statistical work, it isn't. They do what we've done historically. We square those differences. Right? Because if that difference was negative, well, a negative times a negative is a positive. So here, if we had this error being negative 100, square it, it becomes a positive 10,000, just like this other one did. So one functional reason for why we square these residuals is to get rid of the negative sign. The second functional reason for why we would square it is related to the idea of variance. The variance of a variable is the difference of that variable from what we would predict. We usually call that an x bar, that's an average, but notice it's the data point minus the predicted value, and then we square it. Add them all up, and then divide by n, or n minus 1 if it's a sample. So it's an average squared deviation. We're doing a similar thing here. We're taking the difference between a data point and a prediction, and we're squaring it. Then this is going to allow us to try to come up with an estimator that minimizes the variance of our predictions and of our errors, actually. So the reason why we do ordinary least squares regression, that's what OLS stands for, is least squares, is 1, to turn negatives into positives, and 2, because it's related to the idea of variance. Okay, so there was a lot there. Let me rewind. What is it that Stata or Excel is doing under the hood when you say, give me the equation for a straight line that fits this scatter of points the best? And it says, all right, well, I need to come up with, this is the software talking now. I need to come up with, well, let's use our betas. I need to come up with a beta 0 and a beta 1 to minimize how bad my prediction is. So I want to take my data minus my prediction, let's call that y hat. Square those terms just so that we don't deal with negatives anymore. And I want to minimize all of those. So the sum of every single one of my observations, and I seem to have 20 over there. Okay. So the math problem there is minimize this equation. All right. Choose, y hat here is beta 0 plus beta 1x. Choose beta 0 and beta 1 to minimize this nasty looking thing. Incidentally, there is a third functional reason why we do the squaring. And this is because we can use calculus. everyone that's taking calculus knows how to take the derivative of a polynomial. What's the derivative of x squared? It's 2x. Right? You just drop the exponent, make it a coefficient. X squared becomes 2x. So if you want to find the minimum of any function, you want to take its derivative and set it equal to 0, we can take the derivatives of squared terms and then just set it equal to 0. So it becomes solving a linear system, and it's very nice and easy. So people can actually do this by hand. And so back in the day before computers, there was like, everyone wanted to use least squares regression. It was easy, you could do it by hand, minimized variance, it solved a bunch of problems. Now, I should say that there are other alternatives to this. Right? So there's a bunch. The idea behind all of these is usually some variation on a theme. But let's say you got a data point. Some people say, listen, rather than squaring that difference, why don't you take the absolute value? So rather than minimizing the square differences, let's find the least absolute difference or absolute deviation. That makes sense. And computers are good at that kind of thing. You don't need the calculus anymore. Some people say, listen, rather than privileging y, so just try to minimize your ability to predict y, why not draw your line perpendicular? Now that's computationally actually much more difficult. Then again, computers can do the computations for you. Right? So you could minimize the orthogonal or perpendicular deviation. Right? So to calculate this gap and then square it. And then someone said, well, no, let's do orthogonal and absolute. So just take the absolute value of that perpendicular. And it's like a cottage industry. You always have some statistician proposing a different kind of thing to solve. I just throw that out there because you're probably wondering why you don't do X, Y, and Z. These guys are very specialized. They're used in very specific circumstances, and you really have to justify your use of them. You almost never have to justify your use of the standard model, which is ordinary least squares. So that's what we're going to do. All right. Our next question. So you've estimated the straight line. And now what? Like, so what? Great, I can put it on a bumper sticker. Is that what statistics is about? No, there's more. So here I've got some data. I have how much a baseball team paid in salary, so the total payroll, versus how many games that team won. And I ran the regression and I came up with this equation here for the line. Right, so I don't show you the output, I just show you what the line is, the equation of that line. We could stop here. We could just say, listen, there's a relationship between payroll and wins. And here it is. There's your bumper sticker. So we've just summarized the dynamic there between payroll and wins in the baseball leagues. But it does also help us do some prediction. Actually, let me hold off on prediction for just a second. This is interesting for me also, not just because it's on a bumper sticker, but we can see, listen, just in one equation, is there a positive relationship between payroll and wins? Well, let's look at the slope. The slope here is 0.2. Well, that's positive. That's a number bigger than 0. So, all right, our equation tells us that there's a positive relationship between payroll and wins. It's right there. We can run a hypothesis test to say, is 0.2 sufficiently far enough away from 0 that it couldn't have happened from random chance? So that brings up all those hypothesis tests that you did, in your intro to statistics class. If you have more variables that you're estimating, so not just payroll's effect on wins, but maybe some other variable, I don't know what else could go into it, whether you've got a good pitcher. Then you can talk about the relative importance between this variable and this variable. You could maybe compare slopes if you do that appropriately. So it helps with your understanding of how different variables relate with each other. Okay, now finally let's do prediction. Let's say that you're wondering how many wins your team might win if you kind of skimp and you pay very little in salary, like maybe you pay 50 million. Can't believe 50 is a small number. All right, well, plug in 50 into your equation. Let's get rid of that. Plug in 50 right there in for payroll, and some number will pop out. That number is going to be that number right there, which looks to be something around, what, 75. In fact, we can get a specific number. What is the predicted wins? Well, here's our equation again. And payroll, we said, was 50. What if we had 50 for our payroll? All right, well, what's 50 times 0.2? That's 10. So we have 65.13 plus 10, and so we get 75.13. All right, so that's our precise best guess. Our best guess for our y variable, wins, and it's a forecast. It's not a forecast out into time so much as it is a forecast where, you know, if this is the state of the world, if this equation describes baseball today, then we could pick different candidate values for x and come up with a prediction or a forecast for what the corresponding y would be. Now you might think, listen, I've got data around here. What I really want to do is figure out how many wins am I going to get if I'm way off the charts. Like, what if I had 200? Now, here's where I want to ask you to practice a little bit of restraint. Mathematically, what do? You just, you've got your y as mx plus b business going on here. That's your straight line. Just plug in 200 for x, and you get your f of x. You get your y value. So you'll get a number. And it looks like there's one data point at least here. So you're not completely on thin ice. It's probably the Yankees. But I wouldn't extend too much farther out than 200. Once you're trying to make a prediction out where there's just no data to support it, it's getting close to a conjecture. For example, let's say we've got our equation here, for this one here, 65.13 plus 65.13 plus 0.2 times payroll. And the owner comes to you, you're the general manager, and the owner says, how many wins am I going to get if we don't pay our players anything? Okay, now let me just ask you as a human being, how many wins are you really expecting if you don't pay your players anything? I don't know about you, but if you don't pay me much, I don't work much. I'd get really stinking offended if my billionaire team owner decided not to pay me at all. I'm not swinging that bat. I'm protesting. That team is not going to win anything. Incidentally, that's why no team pays zero. Owners would love to pay zero, but they're smarter than that. And so that's why I want you to practice some restraint. Mathematically, you could just plug in a 0 here. And so 0.20 times 0 is just 0. And your prediction would be you'd have 65 wins. That's just not true. You're not going to have any wins. I wouldn't extend this line where there is no data. You just kind of get some like some nonsense. Okay, so that's a little bit of like a cautionary tale, but it can be used for prediction. You just have to do it where there is data. The equation for this line can also answer questions such as, what would happen to the number of wins if payroll changes by a certain amount? Not what if payroll is a certain amount, but what if it changes by a certain amount? So let me show you how to do that. Let's get that pen back. All right, so we have our equation again. So we have wins is equal to, I'm going to drop the decimals, 65 plus 0.20 payroll. All right, now whatever team you are, the owner says, listen, I know we can't go down to 0 for payroll, but what if we were to cut payroll by $10 million? What would that do to our wins? How many fewer games would we win? Or better yet, what, rather than the same players making less, what if we were to replace our players with a new team that costs $10 million less? So they're arguably crappier players. Then how many would we expect to win? Now we're asking, what is the change? So what is change in wins from a change in payroll? All right, now remember, your slope is rise over run. It is the change in your y variable divided by the change in your x variable. Our y variable is wins. Our x variable is payroll. And again, that is equal to our slope, which we said is equal to 0.20. All right, so our nice regression equation can answer our question for us. We basically just have to focus in on the slope and remind ourselves what the slope actually means. Rise over run. All right, so let's keep an eye on this guy right there. Okay, now our question was, what happens to wins if payroll gets cut by $10 million? So the change in payroll is $10 million. All right, so let's keep working this math here. Change in payroll, $10 million. All right, now we can just cross multiply. We've got 0.2, we've got negative 0.10, and we've got x. We've got our unknown. So let's solve for that unknown. Just cross multiply, and we get 0.20 times negative 10 million gives us our change in wins. So in other words, we should expect, let's move that decimal over, and we get our final answer. What's going to happen to our wins? We'll win 2 fewer games next season if we do that kind of thing, which is its own kind of prediction. Not bad from just one straight line. So there's a lot that you can get out of a straight line. This y equals mx plus b, or beta 0 plus beta 1x. Some powerful stuff. It's not just limited to one x variable. In fact, the strength of this approach is that you could have other x variables. So let's just call this one x variable x1 and some other x variable x2. You could have maybe 3 different variables. So 3 things affect baseball performance, wins. You name it. There's actually no limit to how many x variables you can add, as long as you've got enough data to do the computations with. So the power is that you can extend the idea of a straight line into any number of dimensions. Remember, we're fitting a line to a scatter of points. So that's how you draw it on a flat piece of paper. If we were going to go up one dimension, you'd have points hanging in midair. Then, rather than actually fitting a line, like a string, to those points, you're fitting a sheet of paper, a plane. And then we can just keep adding more variables, increasing the dimensionality of the problem. Can't graph it anymore, but you can still do cross products and things like that and calculate averages and correlations, and we can deal with it mathematically. So that's a feature of our method, is that we can do things of almost infinite complexity. Now, people are also still bothered by the idea that we're doing something called linear regression. I've had very smart people say, well, you think the world is linear. I had a dean that said that once, long time ago. He didn't know what he was talking about. Linear actually doesn't, oddly, this is not obvious, it doesn't describe the straight line. Right? If we have x and y, we can actually use the tools of linear regression to plot a parabola, a second-degree polynomial, right? A parabola. We could do third-degree polynomials. We could do logarithmic functions. We could do logarithms in the other direction. We could do exponential decay. There's almost no limit to the kinds of shapes that you can fit using the tool of linear regression. Now let me clean my screen and I'll show you what I mean. When we're doing linear regression, we've got some table of data. We've got data set with y and x, and we got a bunch of observations. So maybe when x is 1, y is 5, and when x is 2, y is 10, but then when x is 3, y was 9. Whatever these numbers are, not important, but you would graph them, right? So when x was 1, y was this number there. Whoa, what happened? Y was a 5, and when x was a 2, y was a 10, but when x was a 3, y was a 9, and so forth. So we get these points, and then we just got to fit a line through them. Now, it doesn't matter what x was, it's just a column of numbers. So let's transform x. Let's square them. Let's square these things and now call it z. So what's x squared? Well, 1 squared is just 1. 2 squared is 4. 3 squared is 9. And now I can just look at the relationship between y and z. Okay, now when z is 1, y is 5. When z is 2, y is, and when z is 4, y is 10. And when z is 9, y is also 9. So something like that. Notice this was on an x scale, this was on a z scale. We've transformed our x, we squared it. So we're changing how widely dispersed these x's are. We're like stretching out our graph. Now, as far as the computer goes, when you just say regress y on z, it looks, does it have a column of numbers? Yes. Does it have a column of numbers? Yes. It just plots them and fits a straight line to them. It doesn't matter that z's just happen to be squared x's, just a column of numbers. Now this is a straight line in this kind of space. But if we were to take this space and then unsquare it, rather than squishing it out, stretching it out like x squares, we're going to take the square root and squish it in. This straight line gets curvature because you're squishing it. And so that's kind of trippy, right? But what does it mean? It means that if you think the relationship between x and y has a curved shape, you can add curvature by just squaring and cubing and whatever kind of polynomial you want on your variables. The variables, it doesn't matter where they come from. It doesn't matter that they might be something else squared, something else cubed. All that really matters is, at the end of the day, to your computer, the only thing that matters is, do you have y's? Do you have some other variable? And then can you plot these on a little scatter plot and draw a line to them? Then you can stretch that thing up and down in any which way to get curvature. Okay, so when someone criticizes linear regression for not being able to capture a complex world, because the complex world isn't linear, that person is a fool, and you should stop listening to him. All right. Well, you can stop listening to me now, too. Thanks for listening, and I'll catch you next time.